So this is a relatively short chapter. And first, we're going to learn about the concept of radioactivity and different types of radioactive emission. Okay, works. So radioactivity normally occurs in nature, right? And up to atomic number 19, which will be potassium included. The isotopes, remember what the isotope is? Oh shit, sorry. Hold on. Remember what isotope is. It's going to show up in a second.
Different number of neutrons.
Exactly. Same number of protons, different number of neutrons. Okay? So, I don't know, like different number of neutrons, yes. So, same number of protons, different number of neutrons. Okay? Now, when the atomic numbers start to rise, some isotopes, the elements with atomic number 20 or more, can be radioactive. Sometimes it's all isotopes are radioactive, but it's rare. Okay? Why? So you have a bunch of positively charged protons, okay, that are stuck within the nucleus. They're all positively charged, and the charges with the same sign, what do they do to each other? Charges with opposite signs do what? Attract, right? Same sign? Repel. So nucleus tries to sort of explode all the time. This repulsion is balanced by neutrons, but at some numbers, neutrons are not enough. At certain ratios, the number of neutrons is not enough. Sounds good? Okay. So, radioactive compounds emit radiation. It can be particles, it can be quants of energy, and we're going to learn what the difference is between different types of radiation. So, the general term for an isotope that is radioactive is called a radioisotope. So when we write down a particular radioactive isotope, we obviously write it the same way we write regular, elements. We include the mass number to identify, and we include the atomic number. So if you refer, if you refer to periodic table, you can see that atomic mass, for carbon, the one that is in the table, is 12, and a change that we can discard, right? So it tells you that the most common and the most stable isotope of carbon is carbon-12. How many protons does carbon atom have? Protons. 6. How many neutrons does carbon-12 have? 6. 6 protons, 6 neutrons, right? Carbon-14. How many protons does it have? 6. Neutrons? 8. Because 14 minus 6 is 8. Okay? So again, so atomic number is protons. Mass number is protons plus neutrons. Am I making sense? So if number of protons is 6 and the number of protons and neutrons is 14, this is what mass number reflects. What is n? If you know that this is 6. Yeah, that's how I got the A. Okay? Good. Now, radioisotopes emit 3 main types of radioactivity. Okay? Alpha, beta, gamma. I know that there are 2 betas. We're going to talk about that. So, alpha particles is essentially the nucleus of helium. Okay? How many, look at helium, how many protons does it have? Helium. 2. How many neutrons? You can check what I wrote here. So this, the atomic number, is the number of protons, correct? Mass number, protons plus neutrons. So, number of neutrons, 2. Does that make sense to everybody? Awesome. Beta particles. Usually it's electrons, but in some types of reactions, they can be positrons. Positron is a particle which by mass is indistinguishable from the electron, but charge is opposite, +1. Okay? And then we have gamma rays, which is electromagnetic radiation. Okay? As a general rule of thumb, ability of radiation to penetrate through a barrier changes from the lowest for alpha particles to the highest for gamma radiation. Okay, good. What is heavier, a proton or an electron or neutron, whatever? Proton and neutron are much heavier than electrons, right? So you would think that alpha particle that contains 2 protons and 2 neutrons, will be absolutely devastating. But it actually has a very low energy. You can think of it this way. It's a weird analogy, but if you would have a choice to be hit by a small bullet or a bus that moves at the speed of like 1 centimeter per minute, what would you choose? A bus, because it will bump into you and that's it. Right? Because the bullet has much greater energy despite that it has much smaller mass. So it doesn't mean that alpha particles are benign. We'll talk when they are dangerous, but beta particles. An electron, so the mass is small, okay? But the energy is what determines how bad the effect of that beta radiation will be, okay? So when do you have a formation of an electron? When a neutron fission is proper. Well, it changes. I'm trying to think about the English word that would. It's not decomposition. Transforms into. It's a breakdown. So a proton and an electron. That makes sense? What is the charge on the left side of that equation? Overall charge here. 0. What is the entire charge on the right side? 0, because plus and minus cancel each other out. Positron, kind of same idea, but it's like an electron but positively charged. So when it's going to happen? Positively charged proton changes into a neutron and positron. Okay, I'm used to this kind of symbols, but this is fine too. Question, Alicia? What is the charge on the left? +1. What is the charge on the right total? +1. Okay. Gamma rays, electromagnetic radiation.
Question.
Go on.
Going back to alpha particles.
Yes.
So when it says it's identical to the nucleus of helium, does that just mean in size? Like it's identical?
It is absolutely identical. It's a nucleus. It looks exactly like a nucleus of helium because it has 2 protons and 2 neutrons. That's it. Okay? Gamma rays are bad. Really high power, okay? So allows the nucleus to drop off some energy. So let's talk about this alpha particle. What is the mass number of an alpha particle? 4. What is the charge of an alpha particle if there are 2 protons in it? 2+. Okay? What is the mass of a positron? 0. It's like an electron, mass-wise. What is the charge? Nope. +1. It's positron, positive. Beta particle. It's an electron, right? What is the mass of an electron? We assume 0. What is the mass of? Well, what is the charge of an electron? So again, we'll get there. We'll get there. Neutron. What is the mass of a neutron? 1. What is the charge of a neutron? 0. What is the mass of a gamma ray? 0. What is the charge of a gamma ray? 0. Okay?
Is that because it's like in the previous slides it's pure energy, so like it has no mass because it's not matter?
Man. So I'm going to try to be brief. So light is both. Light is an electromagnetic radiation. Agreed? Electromagnetic radiation of any kind is both a wave and a particle. Light does consist of particles we call photons. But a photon is not a particle in conventional way. It is like a short blast of a wave. I know it's weird. I think Louis de Broglie, the guy who introduced that idea, I think he was kind of a little nuts when he thought of it. But it explains everything. So photons do not have a mass unless they're moving. They don't exist. A proton or a neutron can exist like sitting, quote unquote, sitting on the table. Photon does not exist outside of light, which is moving. When you think about light, it means a bunch of photons flying somewhere. If there is no movement, there is no light, no photons. There is no mass, intrinsic mass to light. Does that make sense? Yeah, I know. Huh? Well, let's say light, electromagnetic radiation of any kind, from microwave to infrared to light to UV to gamma. Okay. So radiation damages DNA a lot, which means rapidly dividing cells. Okay? Cells that divide rapidly are cells in these various organs, but importantly, what they didn't include is cells that line up the internal surface of your stomach and intestine. Okay? So if you think about the biological effects, the medical effects of radiation, people are exposed to radiation, they form lesions on the skin because skin fails to regenerate. Okay? They develop anemia and leukopenia, a lack of reduced number of red and white blood cells, because bone marrow produces them and bone marrow is wrecked. The ability to produce, now this is mostly for men, because men churn out those sperm cells like million a day, it reduces the sperm count. But think about the lining of stomach and intestine. Those cells divide rapidly because they're constantly damaged. If they fail to divide, the surface of your stomach and intestine, they will become damaged. And what symptom will you develop if your GI tract is injured? Say again? And vomiting and diarrhea, yes. Vomiting and diarrhea. Cramping, that is given, of course, yes. But the advantage is that cancer cells divide super fast as well. So this is why we can use radiation to destroy cancer cells. Okay? Does that make sense? Clear? Now, we do damage. When there's a radiation treatment of a tumor, it does damage the surrounding tissues. Okay? To minimize that damage, there is a profession called medical physicist. These are people with master's degree. It's a graduate school. They have to do residency. What they essentially do, say, Zach is physician. He comes over and says, we have a patient with a brain tumor. We need to treat with certain dose. I, medical physicist, will calculate how to position the gamma ray source, the radiation source, to deliver the necessary amount of radiation in the shortest possible time with a minimal damage to other tissues. Okay? Make sense? Very well paid profession. So how do we protect ourselves from radiation? Well, alpha particles, a sheet of paper. That's it. That's enough. Your skin is sufficient to protect your internal organs from alpha particles. Beta particles. I have to correct this statement. When they say lab coat or gloves, it depends on the energy of emission. Let me explain. For instance, carbon-14, if I remember it correctly, I think it does, it emits beta particles. Okay? Good? Phosphorus-32, another radioactive isotope, also emits beta particles. But when I worked with carbon-14, I worked on the bench. Goggles, lab coat, and gloves were enough protection because the energy of that emission was very, very low. When I worked with phosphorus-32, I had a centimeter thick plexiglass sheet in front of me because the energy is much greater and the damage can be much more significant. So it not only depends on the type. Gamma rays, concrete, or lead. When you go for an X-ray, let's say you go for an X-ray, I don't know, foot, right? What radiation technologists, what do they put on sort of like rest of you? An apron. Is it heavy? There's lead in it. It prevents X-ray, which is a little bit less damaging type of electromagnetic radiation compared to gamma rays. It prevents X-ray from, damaging your internal organs. Go on. The what? Not sure.
It's something that I learned in dental assisting school. They say like with when you emit like the X-ray,
Yes.
there's scatter radiation that comes out like
Yeah. Oh, I see what you're saying.
yeah.
So, imagine that you take a glass of water and shine the light source, like the laser pointer, through the glass of water. When the light comes out, it's going to be bent because of the scattering. X-rays fundamentally aren't different. They're not going to be bent by water, but they're going to be bent by some solid structures in your teeth, for example. So there is scatter radiation that inevitably will damage the surrounding tissues. Okay? Obviously, in addition to protection, physical protection, you can limit the amount of time that you spend near the source and increasing the distance from the source. I violated these two last things when I was working with radiation all the time, because we would just hang out in the radiation room, and I have a shield in front of me, I work with the source, and somebody stands nearby, completely unprotected, and talks to me. We were kids, what can I say? Okay? So again, I remind you, beta depends on the energy. Gamma radiation crosses through human body without any obstruction. Okay? Now, I'm telling you again, carbon-14 will provide you with a relatively low energy beta radiation, which you don't really have to do anything about. Phosphorus-32, I know it's kind of a college trauma. Phosphorus-32, on the other hand, super high energy. Okay? Now this, technetium-99, okay? I'm trying to remember which one is that. It's not tellurium. It is number 43. Number 43. Technetium-99 exists only. Technetium exists as a radioactive isotope only. There are no stable isotopes. And it is often used in the gamma ray cannons that are used in radiation treatment of cancer. Okay? So, heavy clothing. What will it protect against? Beta? Well, alpha, obviously, but paper, lead. I'm just gamma. Lab coat and concrete. Okay. Now, you can measure certain types of radiation using Geiger counter. So this is an old-fashioned Geiger counter. You are going to measure radiation in the lab. You're going to use like fancy Geiger counter, which will connect to the app on your phone, which you will install, which is a pain in the butt to navigate. One of the most confusing apps I've ever seen. Okay, but we'll figure it out. So Geiger counter can only detect beta and gamma radiation. Okay? How does it do it? When beta particles or gamma rays enter a special chamber, okay, the energy of these beta particles or gamma rays turns atoms of gas that fills up the chamber into ions. And these charged ions are registered by the counter. Okay? Good? Does that make sense? Now, what are the units? So I'm going to start actually with Becquerel. Becquerel was a French physicist who first I believe he first observed radiation, and Marie Curie and Pierre Curie, they later sort of explain what's going on. So the Becquerel unit is the International System Unit, which corresponds to 1 disintegration per second. So imagine you have a radioactive object. Let's say it's my mug, okay? It contains something that produces 1 beta particle every second, and it's registered by a counter. So what you're going to have is this, okay? 1 count per second. So that is the unit of radioactivity, then 1 becquerel. 1 Curie is 37 billion becquerels. So radioactivity of, in 1 second, of 1 gram of radium. Are you familiar with the term radium girls? Yes. So women that were painting the dials of the wristwatches so they can be seen in the dark, because radium glows, literally glows in the dark. They had paint that contained radium and was, radiating. But in order to make those really nice little images, ticks, whatever, they used a tongue to straighten the brush. And all of them died of oral cancer. Imagine how little radium was in those paints. 1 gram of radium is insane. Okay? It's an enormous amount of radioactivity. I can give you another example. When I was working, doing my master's, I worked with radioactivity, right? And we received radioactive material every couple of weeks. And usually we received 50 millicurie. 50 millicurie, 1,000th of that unit. It was enough for 5 laboratories. Each laboratory could do 3 or 4 experiments with it. It's an enormous amount of radioactivity. Okay? So, I don't know if you know, but the lab journals, lab notebooks that Marie Curie used, they are kept in a lead safe. They are not safe to be around. They are so radioactive. She died from leukemia at the age of like 50-something. She was buried in a lead coffin. Her body is extremely radioactive. Yeah. Yeah. Like still. You can probably work with that, but you pretty much have to work super heavy protection. Okay? Now, those units determine how many disintegrations happen every second, right? But think of it this way. My mug is a source of radiation, hypothetically, right? Who will be more in danger by being exposed to that radiation? Me or you all? Me. Why? Because I'm sitting closer. So in order to compare the biological effects, here's the term RAD, radiation absorbed dose. For you, the number of rads that you will receive from the source will be less than for me because I am closer. Does that make sense to you? Okay. So, gram of material, amount of radiation absorbed by gram. And radiation equivalent in humans specifically compares different types of radiation. Okay? So I'm going to start from the bottom. Gamma rays. Remember that illustration with a guy walking towards the radiation? Gamma rays, can they penetrate through the human body? They absolutely can, and they will damage the tissues. They will damage DNA, they will damage proteins, inevitably. high energy radiation, for instance, beta particles, or neutrons, or protons for that matter, you can protect yourself, like I did, with a plastic shield. You require less protection, but they still can damage. Now, the damage will not be as bad as from gamma rays, but there will be some. Does that make sense to you? And finally, alpha particles. Remember, pretty much your skin protects. But if you get an alpha particle source inside the body, where there is no protection by skin or clothing, this massive 2-proton, 2-neutron helium nuclei will wreak havoc. Alpha particles on the inside are probably more damaging than gamma rays coming from the outside. Okay? So, to calculate the degree of the damage, you need to multiply the dose by a certain factor that is different for different types of radiation. So, for beta radiation and gamma radiation, the factor is 1. Okay? So, absorbed dose is the same as biological damage. High energy protons and neutrons. Let me ask you this. Gamma radiation. Remember, we wrote down those symbols. What is the charge of the gamma radiation? 0. What is the mass? 0. It has high energy, but the mass is 0. What is the mass of a proton? Yes? Neutron? 1. Imagine that this neutron, or this proton, is very high energy. It will pierce through the human body, even better than gamma radiation. So this is why the factor is 10. You may think, wait, hold on a second. Gamma radiation seems to be more dangerous. Why? For protons and neutrons, we need to multiply the absorbed dose by that increasing factor. You see what I'm saying? Like, why protons are more damaging than gamma? They are not as frequent, but if you manage to be exposed to high energy protons or neutrons, the damage significantly exceeds gamma radiation. Does that make sense? The best illustration is alpha particles. Imagine that tea in that mug emits alpha particles. Are you with me? If I will spill that tea on my skin, I'm going to be okay. But if I will drink this tea, I'm not going to be okay. Because when alpha particles are inside, then we're going to start talking about absorbed dose. When they are on the outside, absorbed dose is 0. Make sense? And since they are so damaging, when nothing protects against them, the factor is 20. Okay? Sounds good? I can give you an example like this. Have you heard the term neutron bomb? It was an idea that was circulated, and I don't know if it was ever implemented because you can't really properly test it. So the idea was to develop a bomb that the main thing that it generates are high energy neutrons. High energy neutrons are extremely damaging to humans, even when they are coming from the outside. And that would basically get rid of people, but would spare the buildings and all that kind of stuff. I don't think it ever came to fruition. Another example, one of my college professors worked in the particle accelerator. You're familiar with that term, right? It's a circular structure in which particles are running at like insane speeds, right? And one of the particles that was participating in the experiment, let's put it this way, was neutrons. And he managed to be inside of that accelerator, it's a giant tube, when somebody accidentally turned it on. And he got blasted with a beam of neutrons. And it eliminated, like he has a scar, and his lung is gone. He has one lung. Okay? And there is a scar because the skin was damaged, but lung was completely destroyed. One pulse of high energy neutrons. They can be extremely damaging. So, you familiar with these guys? Yeah, personal dosimeters. They measure absorbed dose. Okay? Now, why? We are routinely exposed to radiation in buildings, in food or water, in air. Now, the main source of radiation around us in the environment, I'm not including medical procedures, will be cosmic radiation, which largely is contained by the ozone layer. Some small amounts of radioactive isotopes in the food, such as potassium. And have you heard about radon, the gas? Radon is emitted by concrete. Okay. Concrete contains a fair amount of thorium, I believe. Yes. Concrete contains a fair amount of element called thorium, number 90. Okay? The bottom row, second from the left. Actinium, 89, thorium, 90. There are stable isotopes of thorium and there are unstable. When unstable radioactive isotopes of thorium, then thorium naturally occurs in the stuff we make concrete from. Does that make sense? But the stuff that we make concrete from differs from location to location. So it really depends where this concrete came from. Some brands of concrete may produce more radon than others. Make sense? But at the end of the day, what do we check for, like when we do a radon inspection of a house? Which place do we check? Why? Why do we check the basement? Exactly, because it's made out of concrete, right? We don't check upstairs because it's made out of sticks and shit, right? And in addition to that environmental exposure, we also get exposed by, going to x-rays and stuff like that. By the way, one of the exposures that is pretty common is a flight. Like airlines, you are exposed to a lot of radiation when you're in the plane, okay? So I can't quite remember what one, 4 or 5 hours flight is equivalent to, but it's comparable to an X-ray. Okay? So the reason why I don't like nuclear chemists and nuclear physicists, they invented a shitload of units, and you're just like, okay, why sieverts? SV is millisievert. Okay, this is the unit of the dose of radiation that you absorb from a certain procedure, So you can see that over 1 year, you're going to experience the amount of radiation, you absorb the amount of radiation just from concretes and bricks that is greater than one chest x-ray. Go ahead. So when you get an MRI, it's a different type of radiation. It's magnetic field. Magnetic field does not have those negative effects on the human body at all. Okay? There you go. Air travel, point 1. X-ray, point 2. That makes sense. So, you can worry, unless you receive an enormous number of X-rays throughout the year, or you fly 2-3 times a week, long distances, this may skew the results, but overall, it's all pretty safe.
Are those,
yes.
How much is it, like an MS compared to?
I don't remember what, because there's sieverts, there are grays, and I don't remember the conversion factors for those. It is a very small amount. I can tell you that millisievert is a very small amount. When we talk about sieverts, yes, that's when the radiation sickness starts. Okay? So, answer to your question. Less than 0.25 sievert, you can't detect biological effects easily. Now, I want you to remember that radiation effects are often cumulative. If you're repeatedly exposed, even to a relatively low dose, the mutations and the damage to the cells can accumulate over time. Radiation doesn't leave. Okay, so how about I'm gonna address this a bit later when I talk about alphas. For beta and gamma, radiation does not. It comes from the outside, goes through you, leaves. Does that make sense? It doesn't stay in your body. It causes effects, but it doesn't stay. So this is the answer to Zach's question. 5 sievert, 50 median lethal dose of radiation. If you take 100 people, expose each person to 5 sievert, 50 people will die. And others will be very, very sick. Okay? More than 1 sievert, that's what we're talking about. Nausea, vomiting. Greater doses will affect skin, white cell and red blood cell count. Okay? So the larger, the worse. Okay? You can see who's going to survive the nuclear apocalypse. Cockroaches. Like seriously, cockroaches can survive an enormous amount of radiation. Right? Now, this is a very misleading statement. A bacterium is a general term that refers to a certain type of microorganism. If bacteria would be able to withstand this 500 sieverts of radiation, we would not use gamma rays to sterilize food. Or most bacteria are very sensitive to radiation, most of them. But there is a microorganism, more were discovered since then. The first discovered microorganism that could withstand this amount of radiation. Endospores, no. That amount of radiation, nothing. Deinococcus radiodurans. Gamma rays will kill endospores. They will inactivate endospores. Deinococcus radiodurans was isolated from the cooling circuit of a nuclear power plant. My only question, how much pot did you have to smoke to decide to sample water from the cooling circuit of a power plant, hoping to find bacteria there? They found, cultivated them. They are almost unkillable. They were taken to an International Space Station on a agar plate, taken outside in space, returned back to Earth, kept growing. They are insanely resistant. Okay? Now, we do use, why can't you just use sievert, but like, okay, they use kilograys, which is insane, again, amount of radiation exposure, to sterilize food. Okay? Now, I don't remember the symbol. I think it's like a 3-leafed clover, like a little stylish symbol for the food that.
Yeah, it's like a green circle
yes.
with a little plant in the
Yes. Yes.
like,
Yeah. It is a label for radiation sterilized food. And I want to emphasize, food is completely safe to eat afterwards. It's not becoming radioactive. It just, increases the shelf life. Making sense? Because the less bacteria have, the better. There we go. That's the symbol. Okay? So this is the comparison of the irradiated food versus non-irradiated food. You see? Irradiated food increases the shelf life. Questions so far? Well, we're going to talk about half-life, which is a very important parameter for every radioactive isotope. So half-life is an amount of time that it takes a certain amount of isotope to half of it to decompose. Okay? So let's say if we have 20 mgs of iodine 131. After one half-life, we have 10 mgs. Another half-life, 5 mgs. Another half-life, 2.5 mgs. Does that concept make sense? And half-life is a fundamental, it's not a fundamental, it's a constant for every isotope. Okay? So in this example, the half-life of iodine 131 is 8 days. It always will be 8 days. It's going to be 8 days on Earth, on Mars, on anywhere, okay? As long as fundamental laws of universe follow. And you see how it decays. It decays pretty quickly. With a half-life of 8 days, you start with 20 milligrams, and you get to whatever, I'm too lazy to count, much less amount, let's put it this way, in 40 days. Okay? Does that make sense? Now, here are some examples, and I'm going to focus on it. Well, carbon-14, 5,730 years. It's a long time. So the convenience of that isotope is that you can buy it, like it is used for research purposes. You can buy it, put it in the fridge, use it a month later. You're going to have pretty much the same activity. Because what is 1 month compared to almost 6,000 years? Clear? Potassium-40 is insanely long term. It's billions of years. Okay? Radium, but I want to focus on this one. This is strontium-90. Strontium has an atomic number of 38. Please find it in the periodic table. 38. Yeah. Did you find strontium? Sr. Which element sits on top of strontium? Calcium. Elements in the same group, their chemical properties, are they similar or not? They're similar, right? In a human body, where are you going to find most calcium at? Bones. So strontium, if it's taken in, if it contaminates food, right, and it's taken in, your biological systems will process it like they process calcium. And they will deposit strontium-90 in your bones. And the half-life is 38 years, pretty long, and the emission is alpha. So what can you say about alpha source being inside of the body? It's bad. After the explosion at Chernobyl power plant in Ukraine in 1986, a large amount of radioactive compounds, including strontium-90, was sent into the air and contaminated a bunch of food in several regions in Russia and Belarus and Ukraine and even in Europe. People didn't know that and ate that food. And the number of cancers, including osteosarcomas, like cancer of the bone, skyrocketed. Bone marrow cancers, because strontium-90 is now inside. Okay? Does that make sense? I'm going to highlight some of those. So, uranium-238. So if you look at uranium, which is number 92, fourth from the left in the bottom row, very bottom row, fourth from the left, 92. Uranium-238 is the most stable isotope, but it still has some, decay. And what people mine, you know what I'm talking, like when uranium is being extracted from ground, it is uranium-238, which contains a very, very small amount of uranium-235. Uranium-235 is used in nuclear bombs. It is. 238 is fine. You can use it in, 235 is nuclear bomb, right? But again, the fraction of 235 is super low. So what you need to do, it's a bit of a digression, but what you need to do with uranium-238, you need to enrich this uranium, right? Enrich it so the proportion of uranium-235 will increase, and that material will be suitable for actual explosion. Have you heard about Manhattan Project? The biggest secret of Manhattan Project was not how nuclear bomb was organized. It was proposed way before, principle was clear. Technological, engineering things, yeah, they're important, but the biggest secret was to how to enrich uranium. That's it. This scheme of a nuclear bomb, you can find it online. How to build it. The key thing is we're going to get uranium. Make sense? Go on.
So uranium, is that the same thing that lights up green under the black light?
No. That's just fluorescent, different fluorescent compounds can do that. And I want to highlight one more, this one, technetium-99. It is a very convenient isotope if you look at it. Its half-life is 6 hours. So if you need to do a procedure on a patient, you can actually pump the patient with technetium, well, not fully, okay? Give patient technetium and it's going to be gone if you need radioactive label circulating through the blood. Does that make sense? It does not stay. It's convenient. So there's a bunch of medical applications, obviously, okay? Technetium, for example, you can use for the detection of different abnormalities or different things within the body, because with a half-life of 6 hours, it's going to be gone in pretty much a day. Okay? So some examples. Fluorine 18, okay, with half-life of 110 minutes. There's a tomography that's called positron emission tomography. It allows you to get certain images, organs in a particular way. I want to highlight this one. Treatment of thyroid cancer. Iodine is an element that is essential for thyroid hormone production. That makes sense. Thyroid gland is located in front of your trachea, yeah, very close to two carotid arteries. This is a very tricky area to operate. So if a patient has a thyroid cancer, this patient is given iodine 123 or iodine 131, both radioactive, with a relatively short half-lives. These iodine isotopes will be taken into thyroid gland and effectively will burn it from the inside. Does that make no surgery is required? Thyroid gland is just dead. Making sense? And cancer is dead with it. Okay, I'm not going to talk about all of them because, who cares? Again, technetium imaging of virtually anything. Okay? Because if you give technetium to a human being, in 6 hours, this human being is going to have half of it. In 6 hours, quarter. In another 6 hours, 1/8. So in a day, the activity will reduce. The amount of radioactive compound will reduce 16 times. Okay. So it's injectable. Yeah. So scanner will scan the emission, radioactive emission, and will produce the image. And something that I want to highlight. Look at the third column in that table. Type of radiation. You did? Look at the third column in that table. Which types of radiation can you see? Only gamma and beta. Why is there no alpha?
Destructive in your body.
You put it inside and it's going to wreak havoc. Make sense? These rays, so to say, or emissions will leave, will get out of the body and eventually will disappear. Okay? So this is this kind of a thyroid gland, right? Iodine 131 in thyroid. So, positron emission tomography. So, for instance, this one measures some blood flow to the brain. This part of the brain here is much less active because neurons are dead. There's not enough blood flow and it's a stroke. Oh, sorry, Alzheimer's, yes. So, less active. Okay? So this is the reaction for positron emission tomography. You have radioactive fluorine. See that? It decays into radioactive oxygen. Not oxygen 18. No, oxygen 18 is stable. So the atomic number of fluorine is 9. Atomic number of oxygen is 8. How many protons does fluorine have? 9. Oxygen 8. So you need to go from 9 positive charges to 8 positive charges. Making sense? What do? You need a positron because one of the protons, essentially what happens here, one of the protons is converted to a neutron. This is why mass number remains the same, plus a positron. Should put. Okay, good? Making sense? Now, computed tomography, X-rays. I don't know why they put X-ray over here, because it is radiation, but it's not the one that we talked about. It's a little bit less energy than gamma. MRI is not damaging radiation. It's still what's considered like a radiation medicine. But to your question, magnetic field. Okay? Least invasive and least dangerous imaging method available. Good?